Hey everybody, welcome back to Computers and Computations. This week we'll be looking at computational complexity theory. This is a kind of branch of mathematics that looks at the difficulty of problems, and what we'll see is that there are some interesting philosophical upshots of the kinds of complexity classes that these mathematicians consider. And in particular, we're going to try and look at ideas concerning feasibility and possibly creativity as well, and how these might be modeled computationally. So, hope you enjoy the talk. Okay, great. Well, let's get going. In the first part of this course, we saw that all known analyses of computation turn out to be equivalent. So this is really surprising. This is something where we see that there are very limited kinds of, or apparently limited kinds of computation, like Turing computability by a single tape Turing machine, that turn out to be able to model a wide variety of other kinds of computability, like abacus machines, for instance. And this is partly what motivated the Church-Turing thesis. But it's also a bit annoying, right? I mean, everything is either the same in terms of computability or completely intractable, like the halting problem. And what we want to understand in some sense what can be computed, okay? What we can compute. Now, you might think that the kind of interesting cases of can, right, what we can compute, are not just computable given an arbitrary amount of time or space and a Turing machine, but maybe there's a more fine-grained analysis of what can be computable actually turns out to mean. That's part of what computational complexity is directed at. So this is a rough statement of what we're trying to do with computational complexity theory. We're trying to look at how difficult problems are under different models of computation. Okay, and obviously this is at this stage a rather vague idea, but we can make it more mathematically precise. Okay, so what I'll do is first section 1, I'll take you through some complexity classes. We'll then talk in section 2 a little bit about the idea of certain computations being feasible. In section 3, we'll talk about non-determinism as a kind of computation in the associated complexity class NP. And then finally, section 4, we'll talk a little bit about the P versus NP problem and maybe some philosophical implications concerning it. Now, how might we carve up different computable problems into different levels of difficulty or different degrees of ease of computation? Okay, well, the kind of easiness of a computation can be or can depend on at least the following factors, the following kinds of parameters we might consider. So the first is, how bad is the problem instance? Okay, so for instance, if I'm trying to consider an algorithm to solve an n by n Rubik's Cube, okay, there are better and worse instances of that problem. I could give you, for instance, a completed Rubik's Cube, right? That's an instance of the problem. It's just not a very interesting one, and then it takes you one step to solve that. You just hand the cube back to me. So how bad is the problem instance is the first parameter which you could consider. Secondly, what algorithm do you use? There will be different algorithms for different kinds of problem. And then 3, 4, and 5 are going to be the really interesting things for defining complexity classes. So in particular, how much time do we have or do we need to use? How much space do we have or need to use? And what model of computation are we working with? So these are all things that we can tweak and look at how problems are solvable by particular algorithms in these different contexts. So in dealing with 1 and 2, so this is how bad the example can be and what algorithm we're given, we generally want to consider when we say something is in a particular complexity class, the best algorithm we can find, and we look at the worst case scenario, right? The motivation for this is that we're interested in solving problems, even if they're really, really difficult, and doing it as fast as we possibly can. So we rule out the example of the already solved Rubik's Cube and we say, look, what's the worst case of an n by n Rubik's Cube and what would be the algorithm to solve that? Okay. Now, just to note here, best case and average case of the problem difficulty are still really, really important. In particular, if you're a software engineer and you're dealing with mostly best case examples, then you want the best cases always to, if you know you're going to be dealing with the best case most of the time, you want your algorithm to run really well on the best case scenario. Average case is also really important for certain analyses. If I'm working in cryptography, I don't want to necessarily assume that an attacker is going to be presented with a worst possible case of a problem. If I'm just picking out some problem that I'm going to require to be solved, it might be that the average case is actually more important. But for defining complexity classes and stratifying problems, we generally look at the worst case scenario. Okay, and in particular, time, space, and model of computation. These are going to be the really important parameters that will vary for defining different complexity classes. Okay, so we'll talk about models a bit later, but for now, how do we analyze time and space constraints? Okay, so how do we analyze time and space complexity of problems? Well, what we'll do is, given a particular algorithm, we'll look at how the time and space grows as the input size gets bigger. Now, one issue we have here is that there might be a bunch of constants floating around or something along those lines, and we want to get rid of this noise somehow. So useful for this is this thing called big O notation. This is just a way of getting rid of the kind of noise floating around to do with how functions are growing. So that we say that f is less than or equal to O of g if and only if there's some constant c and some n0 in the natural numbers, such that for all inputs greater than n0, these functions, we have that fn is less than or equal to c times g of n. Okay, so the idea is that up to some constant, g overtakes f. It dominates f at some point. This is the idea here. So here's an example. Just putting aside constants for 1 second, if we take the linear function 9001 times x, right, as our function, and we take the function x squared, right, g is going to dominate f, right, even though it's smaller on a whole bunch of inputs. Okay, so the green line here is f of x, the red line is g of x. For instance, at input 1, value is going to be 1, and f's value is going to be 9001. But what will happen is, at a certain point, g is going to overtake f. So let's use this to look at time complexity first. So let t just be a function from natural numbers to natural numbers. We're going to say that a particular Turing machine is t time bounded if for any particular input x, there's a complete run of this Turing machine on x that has length at most t of the size of x as an input. think of x as a binary string, and this is the size of that binary string. So we can then define time t to be the class of problems q such that is some c in n, this is going to be our constant, right? And some c times t plus c time bounded Turing machine deciding the problem. Okay, so we're thinking of a time bound as a particular function from natural numbers to natural numbers, and then we ignore any extra constants that might be floating around in the definition of time t, and this will define a class of problems for us based on the relevant time they take. Okay, and this gives us the resources to define particular time complexity classes. So we let linear time be the union for all the particular constants of time c times n, polynomial time for time n to the c, and exponential time for time 2 to the n to the c. Okay. Now, an observation or an exercise that you might want to look at is that a problem Q in one of these complexity classes, or a problem is in one of these complexity classes, if there's an algorithm with time complexity of the relevant O in the relevant O notation. So here's how you can think of this, okay? So here's an example of what goes on when we have a particular algorithm that decides a problem and runs in less than quadratic time. Okay, x squared will be quadratic time. This is going to be a subset of polynomial time. So as our input size gets bigger, maybe A takes a bit of time on some of the early inputs, but eventually there comes this point where A is dominated by this x squared function when we look at the time it takes each time. So here we've got a situation where even though A is running slowly or slower than quadratic time on some early inputs, eventually it's quicker than quadratic time. Okay, so this is going to be in this problem solved by this algorithm is going to be in quadratic time. Now we can do exactly the same with space. So if we take a function s, this is going to be our space function from n to n. A problem q is in space Sn. If there is a constant c in a Turing machine A deciding q such the number of locations on the write tape. So we'll work here with a read tape and a write tape, because we don't want the read tape to get in the way of the analysis of space complexity, and this can be simulated on a regular Turing machine with fairly minimal overhead. So we have a write tape, and to say that something is in a particular space is to say that the number of locations on the write tape that are non-blank, so that have some material on them at some point in the computation, is at most c times s applied to the input length. So taking the same idea, instead of having time, we're taking space here, and we're looking at how the amount of space that gets used grows as a function of the input size. And again, we can use these to define complexity classes based on how the space grows. Okay, so P space is going to be all the computations that use a polynomial amount of space, given all the relevant constants. And X space is going to be the problems that are solvable using an exponential amount of space. Okay, so the idea here is that a problem is in a complexity class, a space complexity class. Using notation slightly, I'll write F space, just in case it uses an OF amount, or maximally uses an OF amount. So where are we? Well, we have these various complexity classes based on time and space considerations. Now, a way this has been philosophically applied is that people often say that the problems in P are regarded as the feasibly solvable problems. Okay. Now, before we dig into this a little more philosophically, let's note that this is obviously a very important notion, the idea of a feasible computation. Philosophically, it's interesting, but also practically so. I mean, things like cryptography depend on it being infeasible to unfold certain functions. There are certain functions or certain problems that are really hard to solve, at least in one direction. That's what makes the encryption strong. So this is a notion, the idea of a feasible computation, that is really, really important for us to get a good grip on. We can make this claim about polynomial time algorithms precise by something called Cobham's thesis. So this is something similar to the Church-Turing thesis in a sense, but for feasible computation. Remember the idea of effective procedure. This is a somewhat intuitive idea. And the Church-Turing thesis says that every effectively computable function is Turing computable. So it makes an identification between effective computability or effective procedures and Turing computation. So a formal class and an informal class. We have the same here, this idea of feasible function or feasible problem, we might say. This is an informal class, and Cobham's thesis claims that those are exactly the polynomial time functions or polynomial time solvable problems. Slight abuse of notation here. Okay, so what is the motivation for this? Well, I think that part of the motivation is somewhat similar to the Church-Turing thesis. So for the Church-Turing thesis, we found that there were various models of computation that all turned out to be equivalent, right? All models of the formalizing the notion of effective procedure that turn out to be equivalent. And I think something similar is going on here, is that we have generally found the polynomial time problems to have feasibly implementable algorithms, not just polynomial time implementable ones, obviously, but we can genuinely do these things for the inputs that we want to use. So there's, again, when we talked about the Church-Turing thesis, we talked a little bit about the idea that there might be something akin to prediction and confirmation going on, or accommodation of data, right? You have this data that all these notions of computation turn out to be equivalent, and this is naturally explained by the truth of the Church-Turing thesis. Perhaps something similar is going on here. We have all this data that all these polynomial time functions turn out to be actually feasibly implementable, and so perhaps we should just identify the two classes. Now, I think philosophically speaking, there's a bit of an issue here, and a lot of the proponents of Cobham's thesis are well aware of that, but I'd like to consider how we might respond to this problem. And this problem is, look, what if I just make the constant enormous, right? So we're dealing with, in polynomial time, we're dealing with O(n) to the c functions, okay, right? But this c here, this could be huge, right? So I could make this C the number of atoms in the number of the universe, right? So this is going to get this is still going to be, it's going to be a polynomial time function. It's going to be a polynomial time problem, sorry, but it's going to, be absolutely enormous and probably infeasible for any particular inputs we consider. So there seems to be, in a sense, a very clear class of problems that are counterexamples to Cobham's thesis, unlike the Church-Turing thesis. Okay, now people have various responses to this issue, but I think it's an open philosophical problem exactly how we do so, and I'll consider some examples of how we might respond to this on the next slide. Now, I think this is a difficult problem exactly to say how we should respond to this issue of constants. And I'm not entirely sure how one should do it. But I think there's three kind of main options that I can see at any rate. So the first is we reject Cobham's thesis in a literal sense and try and provide a fine-grained analysis of the constants involved. So we try and say, look, Cobham's thesis is strictly speaking false, but look, I can tell you what the kind of properties the constants should have in order to be really feasible, and perhaps as an approximation, considering the polynomial time functions is good enough. The second option is to do a similar thing and reject Cobham's thesis in favor of a graded notion of feasibility. So I say, okay, Cobham's thesis is false, perhaps rather feasibility is a matter of degree, and instead we should say that a particular problem is feasible up to some parameter or other, perhaps. And there might be a link between these two. It might be that you can come up with a nice notion of graded levels of feasibility in terms of the kind of constants you're going to admit. I should say, though, it seems really difficult to come up with some kind of mathematically satisfying notion of what is an acceptable constant here. And I think for this reason, partly for this reason, most computational complexity theorists opt for 3, which is to just say, look, it's somehow in principle feasible. Okay. It turns out that there are these unusual polynomial time algorithms that are going to be very, very infeasible. But what I mean is that in some sense, in principle, perhaps removing the restrictions we have due to, the number of atoms in the universe or something like that, these algorithms are in principle feasible. I think this is one way one can go. It's a bit difficult to see what this in principle might mean, and it's a bit difficult to see why it wouldn't extend slightly too far to capture, for instance, all computable functions, which are, these are in principle computable as well. So it's a very difficult balance to strike, and I'm not really sure which is the correct one to pick or if there's other options. In any case, I think partly what has meant that computational complexity theorists are not so bothered by these kind of large constant examples is for all the problems that we found in P thus far, there haven't been any with these enormous constants. So for the practical purposes of analyzing the difficulty of different problems, it seems that P is a reasonably good measure even in practice, even if there's the logical possibility of these enormous constants. So I think this is a difficult open philosophical problem, and I think some interesting work could really be done trying to be more precise about the sense in which we want to hold on to Cobham's thesis or whether we should really reject it. Okay, so earlier when we talked about P and X, and these are complexity classes defined by time and space, we had determinate Turing machines, the standard notion of Turing machine operating in the background. And what we'll look at now is non-deterministic Turing machines. These are Turing machines that admit a little more flexibility in how they operate. Now, just before I go on and define what a non-deterministic Turing machine is and the class NP, let's just mention that there are lots of possibilities for how you can modify the model of computation in this vast zoo of computational complexity classes. So this is by no means the only way of talking about non-determinism in some sense, but it's a particularly interesting one and essential for formulating the P equals NP problem. And so we'll focus on that one here. But there's a whole bunch of different ways you can modify this parameter, even if we're just looking at the one. Okay, so I won't define fully formally what a non-deterministic Turing machine is. To do so, I'd have to get a lot into the kind of deep mathematical formalization. But the idea of them is pretty intuitive. Okay, so a standard Turing machine is something where it has a bunch of states and it's entirely determinate, given a particular configuration that I start in, how that Turing machine will behave. Okay, so I go from one configuration, maybe I write a 1 or something and move to a different state, and that entirely determines the next configuration I get, and so on. And eventually I halt, or I could spin off, who knows, right? And then we have a Turing machine here will accept just in case it reaches the halting state and outputs 1. It will reject just in case it reaches the halting state and outputs 0, or it might never halt, right? This is our standard deterministic Turing machine. An indeterministic Turing machine, you can think of it as kind of a collection of deterministic Turing machines where it's indeterminate which Turing machine will operate at the next particular configuration. So what we end up with is, rather than it being entirely determinate what configuration follows from the previous one, we can have lots of different configurations following, right? So we have a configuration here, and I could go this way, I could go this way, or I could go this way. Once I'm here there is only one I can pick. Here, I might go this way, or this way, and here I might go this way or this way. What I do require, though, is that if I look back along the path, so I say I got to here, I look back along the path and there is a Turing machine that is going to verify that particular path. Okay, so it's a kind of collection of different Turing machines that can be picked at a particular next configuration step. Now, when we get into the definitions of what it takes to accept or reject given non-deterministic Turing machine in particular input, we see the real power of this this model. Okay, so we're going to say that a non-deterministic Turing machine accepts if and only if there is some path that accepts. Okay, so I have this sort of tree of possible ways my non-deterministic Turing machine can go, and just so long as there is a branch through them that outputs a 1, right, and says yes, then that counts as an accepting run. I just have to find 1. Okay, there might be a whole bunch of other paths that don't go anywhere, but just as long as I get an accepting path, we're going to say the Turing machine, the non-deterministic Turing machine accepts, just as long as we can find one, right? A non-deterministic Turing machine is going to reject if all the paths reject. So however I go through this tree, I always end up halting with a 0. Then we'll say that it rejects. And we're going to say that it loops if some branch is infinite and no branch accepts. Okay, if we find an accepting branch, we'll say that it accepts. And if we have an infinite branch, we're going to say and no accepting branch, we're going to say that it loops. So you can think of this as a kind of lucky algorithm in some sense. If I can find my way through and I just get lucky in the Turing machine I pick and I get an acceptance, then the non-deterministic Turing machine is going to see this. Okay, this then allows us to define our complexity class NP, or a whole bunch of complexity classes. In fact, you can just do the same for non-deterministic exponential time, for instance. But we say a problem Q is in NP if and only if there is a non-deterministic Turing machine A solving this particular problem in O of some polynomial time. Okay, so let's reflect a minute on what this means. This means that when we have time and input size complexity, we could be very lucky at each particular point of the input size and just finding like a really fast path through our tree, for instance, right? So we just have to find one branch that accepts. So this looks like a really powerful notion of computation, especially when we think of it given time complexity. Okay, so we have these different complexity classes defined in terms of time, space, and space for both deterministic and non-deterministic Turing machines. Okay, now we know some things about some of the complexity classes I've talked about. We know a lot about lots of different complexity classes, but here's a kind of chain of inclusions that we do know. So we know that logarithmic time, defined how you would expect, is a subset of polynomial time, which is a subset of p-space. P-space and actually non-deterministic polynomial space, or polynomial space for non-deterministic Turing machines, these are actually equal. These are all both subsets of exp, which are subsets of non-deterministic exponential time, and finally x space. Okay. Now, it's an awful lot of inclusions, and you might wonder, are any of these proper? Of all these inclusions, the only ones that are known are that P is strictly smaller than exp. There are problems in exp that are not in P. And also that logarithmic time is strictly smaller than P space. Okay. So although we have a bunch of inclusions, we really know very, very little about what exactly goes on, or what the exact structure of these complexity classes is. And one that's going to be particularly important for us is looking at the relationship between P and NP. So here's our enormously important open question. Does P equal NP, or is P in fact a proper subclass of NP? This is interesting for a number of reasons that I'll go over in future slides, but let's just say a little bit about why it's so significant. So if you think about what P is telling you, this is telling you that there's some kind of deterministic process for solving a particular problem, okay? So we just go down in a completely deterministic way. This takes me from an input to saying yes, no answer, okay? So this is a problem for P that can be solved in polynomial time, okay? Now, if we think of these as the easy algorithms, these are the problems that can be easily solved. I don't have to think about them or work very hard. NP, in contrast, it's not clear that they can be solved in polynomial time because we have this tree-like structure, right? And if I don't go down the right path of the tree, then I perhaps won't I won't get the right answer. But what I do have is that if you give me a particular branch of the tree, right, then that's a polynomial time run of a Turing machine, okay? So there's a sense in which this represents the class of problems where if I give you the solution, right, then then you can check it in polynomial time. So the question is akin to asking, are those problems that are those problems that the solution can be checked in polynomial time? Also the problems that can be solved in polynomial time, right? In other words, is finding a solution just as easy as checking a solution? This is a very significant difference. So there's a huge number of philosophical questions we could ask about the P versus NP question. Scott Aronson deals with some of them in his article, Why Philosophers Should Care About Computational Complexity. There's also some remarks in his Quantum Computing Since Democritus. And Walter Dean has a bunch of nice articles on the Stanford Encyclopedia of Philosophy, and he has one in Philosophia Mathematica that address some of these questions. I'm just going to focus on 2 points here. I think point 1 is quite a mainstream, well-known point. I think point 2 is not so well-known and maybe slightly more philosophical in flavor, although it has been discussed in various places. So first point, practical point. A lot of cryptography depends on using NP problems, right? So you want a problem where if I give you some information, if I give you a particular solution, you can check that the answer was the right one, okay? So the NP problems are really good candidates for use in cryptography because whilst they're supposedly hard to find or hard to crack, they're easy to verify if I give you the right piece of information. That's sort of a very coarse-grained way of thinking about it. But if P equals NP, right, you have feasible algorithms that can break particular NP problems, right? These problems aren't hard after all. They're easy. You just have to be clever enough to think up the relevant algorithm. So practically speaking, a lot of cryptography, particularly public key cryptography, depends on this question. The world would look very, very different if P did equal NP, okay? Second point, and this is a philosophical point, you might think of NP as a formalization of like creatively feasible computable functions. So earlier I talked about NP and finding the particular right way through a tree of configurations as lucky, right? But you might also think of it as like creativity somehow, right? So let's say this is just the only accepting branch of this tree, and I'm some sort of machine, and I see that I could cleverly, I have to go this way. This is the branch I should pick, right? I just have a flash of insight, okay? So if you, and this is a big if, but if you think of NP as some kind of creativity, some kind of ability to pick the right branch out of a range of options, given a flash of insight, let's say, then if P equals NP, then in fact this apparent creativity can all be modeled by some, determinate machine just plodding along, and can do so in polynomial time, and also indeed if you subscribe to the Cobham thesis, then it's a kind of feasible thing to do. All this apparent complexity of given by NP computations can be modeled by just a kind of boring old deterministic computation. So these two problems are brought into even sharper focus by the existence of NP-complete problems. Okay, what's an NP-complete problem? Well, it's a problem that's both in NP, and also any NP problem can be reduced to it. So we talked about reductions earlier in the context of the halting problem, and one proof, for instance, of Rice's theorem was to show that if we had solutions for the kind of properties of languages that were talked about in Rice's theorem, then we would also be able to get solutions for the halting problem. Similar thing goes on here, where if we're given the complexity class NP, right, there are certain problems, these are the NP complete problems, it's a little subclass of NP, that if you give me a solution to that problem, I can translate it into a solution to any other NP complete problem, or any other NP problem. Given another problem in NP, I can find a way to make that other problem about this particular problem. Okay. Now, there's a whole bunch of NP complete problems. Sudoku is one of them. Tetris is another. A bunch of problems about classic Nintendo games have also been shown to be NP complete problems. So there's some very fun theorems out there, as well as very practical ones. But the really interesting point here is that if P equals NP, this means that any one of these NP complete problems can be, in fact, solved by a determinist polynomial algorithm. And so this means that by solving one of these NP complete problems in polynomial time, I have one kind of polynomial time algorithm whose running just permeates to the whole of NP. Okay, so it would extend throughout NP because I would be able to simulate one of these NP complete problems by a polynomial time algorithm. So this is a really this just shows that if P equals NP, you get some really kind of extreme consequences. And I think it's fair to say that most computational complexity theorists work under the assumption that P does not equal NP. But certainly if this conjecture was solved either in the affirmative or in the negative, but especially if it was solved in the affirmative, that P does equal NP, you would just have this huge raft of consequences for various practical and philosophical ideas. Okay, good. So what have we seen in this talk? Well, we've seen that computational complexity theory looks like it might have a lot of philosophical ramifications, and I think there's a lot of really untapped material here. I've mentioned a couple of places where some good work has been done, but I think philosophers have really yet to provide a detailed analysis of the significance of computational complexity theory. From my perspective, there's a whole bunch of questions one could ask, but I think there's two philosophical questions that I'm especially interested in. And one is that, is P a good measure of feasibility, or should we be opting for some other kind of complexity class or similar kind of object to model the idea of a feasible computation? And secondly, was very uncritical about the way I talked about NP as a model of creativity, right? And I think the extent to which NP is a good model of creativity, the idea of selecting the right branch out of a bunch of reasoning, whether that's really the right way to think of creativity is a really difficult but good question to ask ourselves about what the philosophical interpretation of these important complexity classes should be. So thanks very much for listening. I think this is a really rich area of study and I'm looking forward to looking at it some more. I want to say a big thanks to Moritz Müller, who back when I was stationed in Vienna gave me some really good help with this and gave a wonderful course on it. So thanks to Moritz. Okay, thanks for listening and see you all next week.